Hello and welcome to video 1 for lecture 27. In this first video, we're going to introduce Newton's law of gravitation, also known as Newton's law of universal gravitation. But this is the name of the law. This is going to be section 13.1 from Young 14th edition. This lecture video will cover just section 13.1. Okay, so really the point of this first lecture and first section is to introduce the new law. Now, this is a different type of physics law than we have seen before. We have seen physics laws that refer to conservations, so we've seen some conservation laws, and we have seen laws of motion, namely Newton's laws of motion, which explain the relationship between inertia and acceleration, as well as momentum. But the reason I say that this new law of gravitation is so different is because it explains where force comes from. We've discussed what forces do, but we've never discussed why there are forces, okay? And that really gets into a whole number of other questions. But ultimately, this is explaining that direct observation has never been contradicted, that there exists a law of gravitational attraction between mass, okay? This is not explaining why gravity is attracted to gravity. That's a very modern physics question, but this classical physics law tells us that mass attracts mass, thus gravity exists. Okay, so what form does that statement take? Well, it looks like this. Okay, so this right here, this F equals big G times m1 m2 over r squared in the r hat direction. This law, a vector relationship, is Newton's law of gravitation. All right? So what is it telling us? It's telling us there exists a force, a gravitational force, that is equal to a gravitational constant, more on that in just a minute, multiplied by mass 1 and mass 2, and divided by the distance between those masses squared. So to put this into words, this is telling us that if there's an attractive force, well, more in the direction in just a second, but there is an attractive force between two masses, which is proportional to the product of their masses in kilograms, and inversely proportional to the square of the distance between those masses. Okay? So that's the fundamental law. Okay? It follows an inverse square relationship. This is common for these types of forces at a distance, these types of forces that exist out in space. Turns out that that's very evocative, is very telling of the existence of a gravitational field. The parallel to this is an electric field and Coulomb's law, which has a very similar form mathematically. So there's big ideas kind of that we're starting to touch on here. But ultimately here we're just saying there's an observation that mass attracts mass, proportional to the product, inversely proportional to the square of the distance. So I said I'd mention the directionality. So r hat says that force points along the r axis. So remember, r hat is a unit vector, so it has length 1, thus it does not change the magnitude of g m1 m2 over r squared. It only sets the direction, and the direction has to be along this axis. Okay, so this is the r axis. Okay, so here we have that unit vector r hat. A unit vector points along the radial axis. That's the axis that directly connects the 2 points. These are particles, okay? They don't have a defined radius. They're simply a mass particle, okay? So there is the universal law of gravitation. Now, what about this gravitational constant? Well, because the universal law of gravitation is a law, thus it's just an observation that has never been disproven, that constant is called an empirical constant. It is a constant that isn't derived from anything else, but is observed to exist and is measured as accurately as possible. And the accuracy of that value to quite a few significant figures is represented right down here at the bottom. This is G. Okay, this is the gravitational constant. G is equal to 6.67. This is the way I will always be writing it, times 10 to the negative 11, with units of Newton meters squared over kilograms squared. I always think of it as force times square distance over square mass. And of course, you can easily see where those units come from by just thinking about the fact that these two sides have to be equal to each other in units. Okay? The two sides of the universal law of gravitation. So it's a very small constant. It's times 10 to the negative 11. That tells us a little bit something that I won't get into too much, but that gravity is a very weak force. It is by far and away the weakest of the four fundamental forces that we know of in nature. Okay? Okay, so that's our empirical gravitational constant. If we continue down in our key formulas, we have F vector subscript 1, 2 equals the negative of F vector subscript 2, 1. Okay, so this is simply Newton's third law. This is saying the force on 1 by 2 is equal to the negative of the force on 2 by 1. Okay, case in point here. This would be the force on 1 by 2 because it's pointing to mass 2. Okay, that's the direction that the force has to point. It has to be in the radial direction, not the negative radial direction, but the radial direction. Okay, it's an attractive force. And by that logic, using the same coordinate system, the force on 2 by 1 must point in the negative radial direction because it also must be an attractive force. Okay, so this is consistent with the idea that gravity is always an attractive force and also is entirely consistent with Newton's third law. There's an equal and opposite reaction. Okay, so if some particle of mass pulls on another particle of mass, well, then that particle of mass must pull back with an equal force and in opposite directions. Of course, okay? So simply put, Newton's third law holds for gravity. All right? If the sun pulls on the earth, obviously it does. The sun exerts a gravitational pull on the earth. The earth exerts an equal in magnitude gravitational pull on the sun, but of course in the opposite direction. Okay? All right, so last couple of equations are more of just kind of reminders of what we're going to be doing with the universal law of gravitation. So this one here is the idea that we can sum gravitational forces on a particle 1 by simply taking the sum of each gravitational force. So this is the sum of gravitational forces for a system of discrete objects. We'll do an example like that. Okay? So this would be an illustration of that. There are two discrete objects. Of course, here I wouldn't sum anything because each object is only experiencing a gravitational pull from one other object because it can't experience a gravitational pull from itself. But if I say I had a third particle up here, particle 3, then I could sum up the net gravitational pull and its direction by using components or writing an I hat, J hat, K hat notation. And I can find the exact direction that F net from gravity acts on particle 1. Okay? A gravitational force acting on particle 1 due to more than one discrete neighboring particle. Okay? Well, down below, you won't be surprised at all that this is just the idea of summing up gravitational pulls, but doing it for a continuous solid object. Okay? In that case, you can't just sum up discrete mass elements because there's an infinite number of them. So instead, you'll integrate over the volume, or some part of the volume of the object. This is not something you'll be doing too much due to the difficulty of doing integrals that would require us to do that. Namely that we avoid doing multivariable calculus here. We don't do triple integrals, nor work in cylindrical or spherical coordinates. In fact, we don't even really use polar coordinates. So that's kind of a big limitation. Thus, we really won't do much of it other than making some arguments for certain systems that we can kind of solve very quickly using symmetry. Okay? All right. So there is our introduction. And let's go ahead and get into the first example. Okay? So for practice, example 1 is just a plug and chug case of making sure we can run the numbers with using the universal law of gravitation. So I asked here, what is the gravitational force between an average-sized human with a mass of 75 kilograms and the Earth with a mass of 5.972 times 10 to the 24 kilograms? Note that the radius of the Earth is 6,371 kilometers. It's basically the value we'll be using with the 4 sig figs. Okay, although here we're limited to 2 because of the mass of the person. Okay, so that'll be our part A. Let's see what we get. Okay, so I just plug it in. This is the gravitational force on the person. Okay, it's also the gravitational force exerted on Earth by the person. Okay, so we got our gravitational constant, we've got our mass 1, and we have our mass 2, and then we're dividing by r squared. Okay, so make sure to convert the kilometers to meters and then square the whole thing. That gives us 740 newtons. Well, that shouldn't be a surprise at all, right? Because 75 kilograms times 9.8 is 740 newtons, okay? So we'll explicitly show that we can derive G, we can show where G comes from based on the universal law of gravitation. But for now, just kind of take note that indeed this is a consistent result. Okay. In B, then I asked for what is the how does this compare to the gravitational force between the Earth and the Moon? The Moon is 7.348 times 10 to the 22 kilograms, so about slightly less than 1/100th the mass of Earth. All right, and I take the semi-major axis. More about that when we talk about elliptical orbits and Kepler's laws, but it's something like the radius. Okay, and I say here that it's approximately equal to the radius between the Earth and the Moon. All right. And I use 384,400 kilometers, which is interestingly about 60 times Earth's radius. That's because I bring that up because it's kind of just a nice way to get quick ideas of scale about how far the Moon is, especially when we're talking about satellites and high satellites and low satellites and so on, or Lagrange points for that matter. Okay, and so when we run those numbers, even though the Moon is much further away, that multiplying the distance by 60 in no way compensates for the fact that we've multiplied the mass by 20 orders of magnitude, because we went from about 10 to the 2 to 10 to the 22, and so of course we get a force that is much larger, 2.0 times 10 to the 20 newtons. Well, but there you go. There's the gravitational pull between the Earth and the Moon. So that's how much the Earth pulls on the Moon, and that's how much the Moon pulls on Earth. Okay. Now the Moon's pull on Earth matters. Of course, that creates tides. It also means that there is a sort of an acceleration of the Earth, right? It's being pulled on. We'd have to consider the point at which they orbit to be the center of mass of that system, right? So when we're finding the center of mass of that system, it wouldn't be all that close to the center of the Earth, although it's still certainly within Earth's, within the interior of Earth. But it's, so significant force, some significant considerations to make. Corrections, maybe things we could ignore on the surface, but things we could correct for as well. And that's an idea we'll come back to there when we talk about orbits, about how important is it to consider the two objects orbiting a shared center of mass, which is always true, or can we kind of ignore that and just have one object orbiting the center of the other? It's certainly the sun would be a case where Earth orbiting the sun, Earth is really such a small fraction of the mass of the sun that there we probably wouldn't have to worry. Certainly a man-made satellite orbiting Earth, we could use the center of that orbiting system to be exactly the center of the Earth. Okay, with the Moon, we might not want to. Okay, but when we look at the pull from the person on Earth, that's tiny. Okay, 740 newtons feels significant to a person, but does it feel significant to the Earth? Of course not. If we wanted to find the acceleration that the Earth experiences because of that pull from a person, right? So the person jumps straight up and is accelerated down at 9.8 meters per second squared. How quickly is Earth accelerating up towards them? Well, this is something we discussed before. It's simply a matter of Newton's third law, and it ends up being, if you think about it, well, something on the order of 10 to the negative 22 meters per second squared. Okay? Okay, right, let's move on. All right, so this is a great example of just doing the vector process of solving for the net gravitational force acting on a given particle due to two or more other particles. In this case, I have a rectangle. All right, so let's take a look, right? So four masses are arranged as shown. Mass 1 is 10 to the 9 kilograms. X1, that's this distance here, is 10 meters, and X naught, and Y naught is 8 meters, right? So it is not a square, but it is a rectangle. Determine the gravitational force vector acting on particle of mass m at the origin. Okay, so we have a particle of mass m, so that's just 10 to the 9. Then we got, for these three other particles, all that are more massive, 2m would be 2 times 10 to the 9, 3m is 3 times 10 to the 9, and 4m is 4 times 10 to the 9. Okay, so 4 times bigger. So each of these particles is going to exert a gravitational attractive force on particle m, the one in the lower left-hand corner. And this is what it's going to look like. Okay, I'm going to zoom in on this a bit. So if we look at this figure, we can see this would be the gravitational pull on m from 2m. This would be the gravitational pull on m from 3m. And then this would be the gravitational pull on m by 4m. Let's check our expectations here. So I would certainly expect this one to be the biggest because this is the most mass. Now 3m, I might expect this one to be the second biggest, but I'm not quite sure because it's significantly further away because it's a hypotenuse distance away rather than one side of the rectangle. 2m has the least mass pulling, but is closer to 3m, so maybe we'd expect these two forces to be similar in magnitude, and that's kind of the way I've drawn them. If I want to find the net force, I can take a tip-to-tail vector approach to get an idea about where it's going to be, and so you can see here that it would be pointing, it'd have some length comparatively to the other ones, and it would point up at an angle that would certainly have to be greater than 45 degrees because this 4m is going to make it more vertical than horizontal. Okay, so we'd expect phi to be greater than 45 degrees and beta to be less. Okay. All right, and notice my angles here. I've labeled these two. They sum up to 90 degrees, and the reason I'm not calling either of them theta is because I reserve theta to take my components of the gravitational pull on m from 3m. In fact, force 3m is the only force vector I'm going to have to worry about taking any components for because the other two are going to lie exactly on axes, the x and y axes that is, which of course will make them dealing with them quite easy and not require components. Now, in part A, we want to determine the gravitational force vector acting on the particle of mass m at the origin. Write this vector in I hat, j hat notation. We don't have to worry about a k hat because there was nothing going on in the z-axis. All right, so let's get this started. So f net is just going to be the sum of those vectors if I write it as a vector equation. I'm going to want to then split this into components so I can actually solve it because otherwise really this is just going to tell me the tip to tail. Okay, so I split it into x and y components. So in the x direction I got the force from 2m, and I've got a component of the force from 3m. In the y direction, I have the force from 4m, and a component of the force from 3m. Everything's pointing in the positive direction, all right, so we're good there. All our negatives are accounted for. Now I'm going to go ahead and express sine in terms of the lengths. This is going to make my life a little bit easier. It's a good approach for a problem like this. Okay, now I could have just come up with it. I was given the exact value, so I could have literally just solved for theta, save the number in my calculator, and just kind of move numerically. But here, instead of doing it numerically, I'm going to keep things symbolic to show how they simplify. Okay, so this is sine theta expressed as just opposite over adjacent. This is this theta, of course. Opposite of adjacent would be y over the hypotenuse. And then cosine theta is going to be adjacent over hypotenuse. Of course, just x naught over the hypotenuse, which comes from the Pythagorean theorem. Okay, so now let's look at our f net x. Zoom out a tad. So here, you can see that I simply took the expression that I wrote above and expanded it out a bit. So the force from 2m would look like this, right? Because it's constant, universal constant of gravity, and then m1 and m2, which in this case is m and 2m, and then the distance between the two squared, x naught squared, okay? And then I do the same sort of thing over here, okay? So that's the gravitational force. This would be the overall magnitude of 3m, okay? So that would be that distance there. But of course, I just want the x component, so I want this smaller x component of 3m, so I have to multiply it by, I have to multiply by cosine, okay? Cosine theta, because that will give me my x component based on the way I've chosen to measure theta. So notice what happens here, right? So here, this is just the distance between them, and it's squared, right? So that's what it looks like the Pythagorean theorem. But of course, sine itself, or cosine in this case, also refers to that same distance, because of course it's opposite over hypotenuse. Well, it's the same darn hypotenuse, isn't it? So they'll combine together. And so what I end up with is y naught squared plus x naught squared to the 3/2 power for my second term, for the force from 3m in the x direction. Okay? All right, good. So you can hopefully see how that cleans up. And I factored out the like terms of g and m squared, because it only worked out to factor out m squared because all the other masses were in terms of the corner mass. Okay? So then it's very similarly in y. The only difference is there I have sine theta expressed in terms of opposite over hypotenuse. Okay, and then it simplifies to something that looks quite similar. Of course, we can already see it's going to be bigger though, because it's got the 4m in the y direction. We only have the 2m in the x direction. Okay, so then I'm going to go ahead and write this in I hat j hat notation. So what will that look like? Okay, well let's plug in what I got. All right, so this is basically as simplified as it's going to get, and so I go ahead and just plug everything in. Okay, time to plug in the numbers, and I do that in the x direction, which is attached to the I hat, and then I do it with the y component, which is attached to the j hat. Okay, so there is my final f net vector in I hat j hat form. Okay, and this would be in terms of newtons. Now here I was able to get my values in terms of newtons that were kind of really nice didn't have to worry about, writing them in scientific notation. And that's because I went out of my way to make the masses incredibly huge, right? These are particles that each weigh 1 billion kilograms. That's necessary because, again, remember that the gravitational constant is so small that unless you have something like 1 billion kilograms, you're not going to get gravitational forces that are going to be on, the noticeable scale of a few newtons, right? Kind of on a human scale, okay? So, but good luck finding something that you could really approximate as a particle that weighs 1 billion pounds, 1 billion kilograms, okay? All right, so then if you want to find the magnitude, I simply just use the Pythagorean theorem, but on F net. And we get then that the net force has a magnitude of 5.44 newtons. All right, looks good. And then if I want to find the angle phi, I get 65.1 degrees. Okay, and we are asked for beta, which is the angle, if you look at part C, which I didn't read. I didn't write it here. But part C is in what is the magnitude? Oh, the angle of the vector with the vertical axis. So it's actually not part C, it's just the end of part B. And so since I want the angle with the vertical axis, I want beta. Okay? I could have just literally took tangent inverse of f net x over f net y, but I went about doing it this way and subtracting what I called phi from 90 in order to get beta. All right? And indeed, like I said, beta is less than 45 degrees, which means the net gravitational force vector on mass m is pointing more vertical than horizontal. All right, so just practice with vectors, pretty straightforward. I hope you wouldn't have any issue with a problem like this, but it's always good to practice it. Okay, all right, so I have one more that I want to show you, and then we'll conclude this video lecture. All right, so here we have a solid object, kind of the natural other system here, since we just looked at a system of discrete objects. All right, so how do we approach this? Okay, well, in this picture, I kind of drew it out so I could call attention to the geometry of the system. And over here, I'm just kind of pointing out more of a pictorial representation. But these two pictures just complement each other. They're showing the same thing twice in two slightly different ways. The idea is that we have a ring. So a mass m is ring-shaped with a radius r, as you can see. Okay, mass big M. A small mass little m is placed at distance x along the ring's axis, as shown in the figure. Right, so it's along the central axis. It's important. What is the gravitational force on the mass m due to the ring, and what is the gravitational force on the ring m due to the mass? Okay. So we need to find that gravitational force due to the ring. So let's think about it. We've got some mass element of the ring up here, dm. We have another one down here. Those two ones on either far end would be a distance of x squared plus r squared because of the triangle that's made here. Okay, that makes sense. We could think of ones that are like this that would also be distributed in the same way. Okay, but here's the thing. If we think of this in a two-dimensional case, we can see then that there would be a certain amount of mass pulling in the negative fy direction and another amount of mass pulling in the positive fy direction. Likewise, if we thought of z, right, we'd have the same sort of result, and they would be symmetric. There would be just as much pull down as up, or in as out, okay? On the other hand, the gravitational pull in what I call the x direction would sum up, right? Because these two darker vectors are the gravitational pull from these two mass elements, and we can see that their vertical components of those vectors is equal in magnitude but opposite in direction, whereas the horizontal components are equal in magnitude but in the same direction, so they actually will add together rather than cancel out. Okay? All right, so we need to integrate because the ring is not a particle. So this is the expression for finding the total force, okay? And then dF, right? This is just we could think of this as a force element. This is the force due to dm, right? As you can see here. Oops. All right. And since dfy components cancel, only dfx components are non-zero. So that means that this expression would just be the x component. So we'd only be looking at the cosine. Again, that's because of theta there. Cosine is the adjacent part of that triangle, right, of this hypotenuse. Okay, so that's where the cosine comes from. I'm going to do the same thing I kind of did with the discrete system. Okay, and so then we get an expression right here, x squared plus r squared to the 3/2. All right, so then we're just going to integrate from 0 to m. Okay, so when we look at this, all of these things, r is independent of m, x is independent of m. Oh, that's interesting, right? So that's actually telling us that when we do the integral, we don't have to actually, there's nothing that's a function of m. We don't have to rewrite m in terms of anything, okay? When would that be different? Well, what if the ring had a non-constant density, okay? Well, then we would have a density function that would be a function of theta, right? Because we'd have to integrate around the ring, and we'd have to use some polar approach to integrate around the ring. But here we have a uniform density ring, So we just go from 0 to m times dm to integrate over the entirety of the ring due to the symmetry argument we made. And so then the final result is just this. The dm just becomes m, as simple as that. Okay? So this would be the total gravitational pull from the ring. It did simplify quite a bit, but the result is actually still quite nice. It would tell us exactly how much that ring would pull on the mass. And that's a different pull, by the way, than say if the ring was replaced with a sphere. So the pull is unique to the ring. It does indeed encapsulate the effect of having the mass distributed in a ring in a uniform way. Okay? So, and no numbers in this case, just a symbolic result. So I haven't saved much for your practice from this first half of lecture 27, but I am going to go ahead and save example 4 if you want to give this one a try. This is another solid, and you can think about how you would approach this. There's a way to do this quite simply if you kind of think about not having to integrate, but just think about kind of how can you simplify the system. Okay? All right, well, thank you very much for watching, and please tune in for the second half of lecture 27.